Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Bender's decomposition using graph modeling and multi-parametric programming. Research developed by Parth Brahmbhatt, David Cole, Victor Zavala, and Styliani of Ramadou. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. In 1962 J. F. Benders published his theory oriented to optimization of large-scale problems. The fundamental idea is the partition of a problem into two subproblems of reduced complexity based on the division of the variables like coordination variables and subordinate variables. The solution of the original problem is obtained by the coordinated solution of two complementary subproblems. The coordinator linked to the coordination variables, and the subproblem linked to subordinate variables. Bender's decomposition using graph modeling and multi-parametric programming. Bender's decomposition, BD, is a widely used method for solving large, structured optimization problems, but its performance is affected by repeated subproblem solving. A flexible and modular algorithm to accelerate BD is proposed, which will be called BDGM. The structure of the problem is expressed by a modeling abstraction in graph theory, in which the nodes represent optimization subproblems and the edges represent the connectivity between subproblems. A key innovation is that it incorporates multiparametric programming substitutes, MP, for subproblems in the nodes, which exactly map the analytical map of the subproblem-solving space. The use of MP surrogates allows us to replace subproblem solves with fast lookups and function evaluations, for primal and dual variables during the iterative BD process. BDGM is equivalent between the classic BD cuts and those derived from the MP. Multiparametric programming substitutes, MP, is an optimization technique that solves problems such as explicit functions of input parameters. It has received significant attention in process systems engineering, multi-level optimization, and robust predictive control optimization. By parameterizing optimization problems, MP allows the derivation of optimal solution maps, for primal and dual variables as functions of the input parameters. This structure allows for efficient implementation of the solution strategy, as it boils down to the evaluation of a function once the appropriate critical region has been identified. MP surrogates for node subproblems in BD. It consider optimization problems where a node is replaced by a MP surrogate. Using surrogate models to represent subproblems in nodes provides an avenue for standardizing modeling problems that contain heterogeneous components, since surrogates provide a unifying modeling abstraction for all components. The use of surrogate models to represent node subproblems provides an avenue to standardize the modeling of problems that contain heterogeneous. This can help streamline modeling and gain insight into model and algorithmic behavior. Key innovation is that the incorporation of multiparametric programming, MP, substitutes the subproblems in the nodes, which maps represents the exact analytical map of the subproblem-solving space. The use of MP surrogate allows subproblem solutions to be replaced by quick lookups and function evaluations, for primal and dual variables during the iterative BD process. BDGM is implemented in the open-source software package Plasmo Benders. JL. It is applied to a two-stage stochastic scheduling problem, 2SP, to make optimal decisions about capacity expansion in the face of market uncertainty. Single and multi-cut BD variants, and the use of MP surrogates, achieve significant reductions in subproblem resolution time, preserving BD convergence. BDGM highlights advantages in solution analysis and interpretability that allow the monitoring of critical MP regions. Specifically, it shows that they reveal how decisions evolve geometrically throughout the BD. The results demonstrate that combining surrogate modeling with graph modeling offers a promising and extensible foundation for BD that leverages structure. By breaking down the problem into more manageable subproblems, BDGM overcomes the scalability issues. Finally, the use of MP substitutes provides a unique and modular optimization framework that allows the representation of heterogeneous node subproblems as objects modeled with a homogeneous structure. Multiparametric programming, MP, is an optimization technique that solves optimization problems by parameterizing optimization problems. MP allows the derivation of optimal solution maps for primal and dual variables, as functions of the input parameters. The solution map for MP problems is characterized by critical regions, CR, which are subsets of the parameter space where a given set of constraints is active. When the target function is linear or quadratic, and the constraints are linear, these regions divide the space of feasible parameters into polytopes, and within each region, the optimal solution is described by an affine function of the parameters. This structure allows for efficient implementation of optimal solution strategies, as the solution reduces to a simple function evaluation once the appropriate critical region is identified. The graph shows the decision trajectory in the space of critical regions for the time step 5, using BD single cuts. To demonstrate the usefulness of MP surrogates for BD, we focus on two-stage stochastic programming problems and the two-level tree graph structure. However, the proposed approach is general and can be applied to more general graphs. In BD, the problem is divided into a master problem and scenario-specific subproblems. The figure shows the graph representation of the problem solved with BD. The master problem is stored on a subgraph, 0, and each subproblem is stored on independent subgraphs 1, n. Edges contain the constraints with complicating variables. The user can set subgraph 0 as the master problem, and OptiGraph will recognize that subgraphs 1 to n are the subproblem subgraphs. The user configures the solver as the optimizer for the subproblem corresponding to a specific subgraph and subsequently retrieves the MP solution data directly from the solver. Once optimize is called on the subproblem, primal and dual information queried from the solver will be returned internally from the MP solution functions. Julia for mathematical programming, JuMP, is the industry standard modeling language specific to Julia. It allows you to write optimization problems with a natural mathematical syntax and solve them using a variety of back-end solvers. The most common JuMP solvers used are IPOpt, nonlinear; HiGHS, linear and integer; Gurobi, general commercial; and Clarabelle, convex. To implement the MP surrogate models within the graph modeling framework, it is defining a custom solver in Julia such that no changes are required to the existing software of Plasmo.jl and Plasmo Vendors.jl. This is a custom solver in the sense that it has defined its own methods in the Julia code that uses the MP data to solve the optimization problem and query primal dual information, independent of typical LP solvers such as HiGHS or Gurobi. Plasmo.jl build the optimization model as a graph, and Plasmo Vendors.jl manage the Vendors decomposition steps, and a custom Python solver for MP that connects to the system. The algorithmic framework was implemented in Python open source software for MP surrogates, and Julia for graph-based modeling in BD. The integration of programming environments highlights the modularity that allows the use of MP surrogates. The subproblem can be formulated and solved as a MP problem after defining parameters. The solution of the MP problem represents the affine function defined for each critical region as the corresponding inequality matrices, for each critical region, which represents the entire map of optimal solutions of the subproblem. For any realization of the defined parameters, it is saved in Julia. After loading the MP model solution, the full optimization problem is stored in Plasmo.jl. The master problem and each subproblem are placed in separate subgraphs with linked constraints between the master problem and each subproblem. Each subproblem is independent of the others, so that each binding constraint only links to the problem's master subgraph and each sub-subgraph to the subproblem. Once this structure has been created, can be applied Plasmo Vendors.jl that takes the user-defined OptiGraph structure to set the master subgraph. Once this subgraph is set, Plasmo Vendors.jl detects the downstream subgraphs, fixes the complicating variables in the subproblem subgraphs, and adds the cost to go. At a given Vendors iteration, after the master problem yields a solution, the goal is to generate an optimality cut. The BD cut is a linear approximation of the subproblem's value function. An affine function can be expressed as the sum of linear functions plus a constant. A crucial property of MPLPs is that the dual variables, like the primal solution, are affine function of the parameters. Within a single critical region, the set of active constraints in the optimal solution is constant. This allows us to formulate the subproblem as an equivalent equality constrained LP for that specific region, because the matrices that define the problem contain only the rows from the original problem that correspond to the active constraints in the region. To find the duals, this function can be derived explicitly by analyzing the optimal Karush-Kuhn-Tucker (KKT) conditions of the subproblem and the definition of the Lagrangian function. OptiGraph is a domain-specific language for graph analysis, developed as a research project at Stanford University's in the Pervasive Parallelism Laboratory. The figure on the left shows an example of OptiGraph abstraction, where the optimization problem is divided into the nodes and edges of the graph on the right. The OptiGraph abstraction can capture hierarchical relationships within problem structures and form nested subproblems. Its ability makes it a flexible modeling tool for embedding subproblem surrogate models into nodes. Any subproblem in a node can contain, or be replaced, by a surrogate model, such as an MP program or a neural network. The general outline of the proposed framework is summarized in Algorithm 2. Replacing LP solutions with simple related assessments makes the subproblem phase almost cost-free, while maintaining convergence guarantees, as the cuts do not change. In its most basic form, the problem description is the long-term capacity expansion and production planning problem with fixed charge expansion costs that can be stated as follows. Given an extended network of continuous production processes and chemicals, the primary goal is to determine the optimum selection of processes and how their capacities should be expanded over a future horizon consisting of a horizon planning of several periods. The figure shows the superstructure of the plant transforming chemical 1 and chemical 2 into the final product chemical 3. Each of these three chemical-related quantities is considered uncertain, giving a total of 6 uncertain parameters, 3 multiplied by 2. In addition, the operating cost parameters for each of the three processes and the cumulative capacity parameters for the first stage are also treated as inputs to the model. The computational statistics for problem instances table provides a detailed breakdown of the problem size for the case study with 2,000 scenarios, 3 processes, and 3 chemicals, across the different time horizons. Although in practice prices, demand, and availability are usually statistically correlated, the case assumes that they are mutually independent. Each scenario is treated as an independent realization of uncertainty with a corresponding probability, which is used in the expectation operator in the stochastic model. The average values of parameters used table for the base case table provides lists of the average values used, where the rows correspond to processes from 1 to 3 and the columns to periods, 1 to 4. To generate the complete set of scenarios, the sample values were synthetically generated from normal distributions centered on the mean, using 10% of the mean as the standard deviation for each distribution. The Table 3, lower and upper cumulative capacity bounds per period expansion limit, provides the lower and upper bounds for capacity expansions. And the Table 4, stoichiometric consumption and production coefficients, provides the stoichiometric consumption and production coefficients for each process. The figure shows the graphical structure of the capacity expansion planning problem. Over time, the master subgraph of the problem contains the decisions of the first stage. The capacity decisions of the second stage are linked, by binding constraints, to the subgraphs of the scenario in each period. The problem was implemented as a graph model within OptiGraph, programmed with Julia, and can be solved with different solvers. The problem of the first stage is in a subgraph called a master, which covers all the periods represented as a node. Each of these nodes is also linked to the previous period of each scenario and then added as separate subgraphs, each linked to a node. These periods of the scenario are linked to the master problem by limitations, edges, which contain the complicating variables. This results in subgraphs of subproblems that can be solved independently and in parallel. The graph model was solved using the MP data and the Julia model. To ensure our results are reproducible for researchers who may not have access to commercial software, we also included HiGHS, a leading open-source solver. For consistency, all tests were run using the Julia model. Solves were done with both multi-cut and single-cut Bender's approaches. In the case of the BD single cuts, the figure shows the subproblem solution time versus the number of scenarios for different time horizons. To analyze the behavior, instances were run using MP benders, high GHS benders, and Gurobi benders as a MILP solver to solve the master problem. The subproblems were solved by comparing MP benders with direct solutions using Gurobi benders and high GHS benders. The primary motivation for examining this variant is to assess the performance advantages of MP benders surrogates in settings that require many benders iterations, as is typical with single-cut formulations. This observation suggests that the computational benefits of MP surrogates become increasingly prominent in scenarios where the BD must generate a greater number of cuts to converge. Notably, the subproblem solve time using MP benders is significantly lower than Gurobi or high GHS solvers, and this difference is pronounced compared to the multi-cut case. Figure shows the subproblem solve time versus number of scenarios for different time horizons T, for the multi-cut case. Figures 5a to 5d illustrate the computational results for DB multi-segmentation with planning horizons of 5, 10, 25, and 50 years. Subproblem solution time is reported for different numbers of scenarios equal to 50, 200, 500, 1000, 2000, comparing the critical region query method based on MP benders with direct solutions using Gurobi benders and high GHS benders. Across all cases, the MP benders approach consistently yields faster subproblem solution times, particularly as the number of scenarios increases. These performance improvements are primarily due to the avoidance of repeated LP solves by querying precomputer-defined solutions from critical regions. It is important to note that the reported subproblem solution times for the MP benders case include the one-time overhead of computing the critical regions. As a result, for smaller scenario sizes, the MP benders approach may not outperform the direct subproblems of Gurobi or high GHS, as the relative impact of the overhead generation time of the critical region is more significant in such cases. Figures 7 to 10 depict the trajectory of the first-stage capacity decisions as they evolve over the BD benders iterations. Each point represents a solution from the master problem, which is guided by cuts from 500 scenarios. Each subplot corresponds to the decision variable for a specific time, showing how the algorithm searches the critical region space for that decision. This visualization reveals several key insights. Convergence behavior. In the multi-cut case, the iterates tend to converge more directly toward the final solution, traversing fewer critical regions. This aligns with the theoretical observation that multi-cut benders converges in fewer iterations due to richer feedback from the subproblems. Decision consistency. At certain time intervals, such as periods equal to 3 or T4, iterations remain confined to a single region, or a small number of regions. This suggests the robustness of the resource structure with respect to small disturbances in the master decision. In fact, resource decisions show local linear stability. Aggregation effect. The single-cut formulation requires more iterations and exhibits more oscillatory behavior, by aggregating all subproblem feedback into a single surrogate. Policy transparency. Since each region corresponds to a fixed active set of constraints, it is possible to determine why a particular resource policy is optimal for an entire class of scenarios, the critical region, by identifying binding operational constraints. This allows for a richer post-optimal analysis, identifying which constraints dominate the solution's behavior under different uncertainty realizations. The figure shows the multi-cut evolution of first-stage decisions over BD iterations for a problem with 5 periods and 500 scenarios. Each subgraph shows the iteration path for the decision in a specific period, from 1 to 4. The figure shows the multi-cut evolution of the first-stage decision on BD iterations last time equal to 5. The graph shows the decision trajectory in the space of critical regions for the time step 5. The figure shows the single-cut evolution of first-stage decisions over BD iterations for a problem with 5 periods and 500 scenarios. Each subgraph shows the iteration path for the decision in a specific period, from 1 to 4. The figure shows the single-cut evolution of the first-stage decision on BD iterations last time equal to 5. The graph shows the decision trajectory in the space of critical regions for the time step 5. The figure shows the evolution of the upper and lower bound for both multi-cut, blue, and single-cut, red, BD algorithms for a representative problem instance of 5 periods and 500 scenarios. This result confirms that the MP-based Bender's approach converges to the optimal solution. Diamond markers indicate convergence to the optimal value. The results shown are same for the MP Bender's method using Gurobi. This also illustrates that MP surrogate provide guarantees of optimality, since the primal and dual variables are optimal, not approximate. Taken together, these insights offer a new perspective on stochastic optimization algorithms, not just as iterative black box solvers, but as structured geometric processes that navigate a known, albeit high-dimensional, partition of parameter space. This geometric lens can support better debugging, policy interpretation, and even sensitivity analysis regarding scenario inputs or problematic data, directly addressing the need for greater explainability in stochastic optimization. Although computational accelerations are more pronounced in many scenarios, the framework is still competitive for medium-sized problems. The improved interpretability of the solutions offered by critical region tracking provides a significant advantage that is independent of the scale of the problem. Although computational accelerations are more pronounced in many scenarios, the framework is still competitive for medium-sized problems. Albert Einstein thought that imagination is the highest form of research. Thank you for your attention.